Hello and welcome back. Hopefully you had a really good weekend and you've gotten a really good start on your third assignment, which is going to be the majority of graph algorithms, which I hope to be done with by the end of tomorrow at the very latest. But today we're going to continue with what we left off with on Friday, Kruskal's algorithm. Remember that Kruskal's algorithm builds a minimum spanning tree, that is a tree that spans a graph, a weighted, undirected graph generally, by sorting all of the edges in non-decreasing order and then taking the minimum one each time. And as it builds this tree, it checks to make sure that it is not that it is acyclic. And if choosing that edge would induce a cycle, it does not choose that edge, and then it moves on to the other and the next edge. And we saw an example of that on Friday. What I wanted to do is I wanted to go over that again, not the example again, but revisit Kruskals with a little bit more detail. The first item that we're going to do today is we're going to actually formulate a proof of this. Now, this is kind of a trivial proof, at least there's not much to it. It's kind of it's a mixture of induction and proof by contradiction. There are a couple of details that I'm going to omit here. One of those details is that you can assume that all of the edges have a unique weight. If not, then of course, then you can augment them by adding a little bit of a weight here or there, or something like that, so that you do have that condition. But we'll assume that by way of contradiction, Kruskal's algorithm did not produce a minimum spanning tree. So what we're going to do is we're going to start out by looking at all of the edges that were used or considered by Kruskal, right? So E1, E2, E3, dot, 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 up to some EK. Now that's not all the edges. I'm just supposing that there's a sequence, and then you can go on with the sequence. And we're supposing that the Kruskals did not produce a minimum spanning tree. A minimum spanning tree. Remember, they're not necessarily unique. So let's write down all these edges in the same order as before. As before. And what we'll do is we'll assume that they're different somehow, because otherwise, if they're the same edge set, then we're already done. There is no contradiction. So by way of contradiction, we're assuming that they are different trees. Now what I'm going to do is I'm going to highlight these edges. Now this is we're going to assume that these are the edges in which they disagree. This edge EK, that was in one of these trees but not the other, and vice versa. It was not, or vice versa. It was not in one but it was in the other. So now let's go ahead and take some cases here. A. We'll suppose that this edge was not taken by Kruskals, right? And that it was taken by the optimal binary search tree. So I'll just rewrite this as a minimum spanning tree. All right. First of all, we're going to observe that this is not possible. Because the way that I wrote down these edges, as I said, hopefully I said it, maybe I skipped it, that we're going to write them down in the order in which Kruskals considered them. And then it's the exact same sequence down here, and they have to differ at some point, otherwise these are in fact equal, right? So Kruskal did not choose it, but the minimum spanning tree did, right? Remember the condition for Kruskal choosing to include an edge or not include an edge. Kruskal would not have considered this edge if it induced a cycle, meaning that in the inclusion of E sub k with all of these edges prior to it means that there's going to be a cycle. It would imply that MST, the minimum spanning tree, has a cycle, right? Contradicting the fact that they're different and that this is in fact a minimum spanning tree. So case B, it must be the case that Kruskals took this edge, but the minimum spanning tree, that necessarily has lesser weight, did not. Okay? All right. So there's this edge here, EK, that has these endpoints, say A and B. right? Somewhere in the graph, and you can imagine this as the graph over here. Okay. Now, suppose that we've got this. Now, this is not in the minimum spanning tree, right? Again, because of our setup here, but it is a spanning tree, so A and B have to be connected by some other path. Right? I'm going to draw. Imagine that I've drawn that path over here somewhere. Right? And this is the path P in the minimum spanning tree that connects A and B. Otherwise, it would not span the graph. Okay. Now, there must be some other edge over here. I'm going to call it on this path called E sub j, just because I can't use E sub k anymore. Okay. Now, my first observation is that E sub j, the weight of E sub j, is necessarily greater than the weight of E sub k. Okay. Since if all otherwise, if all edges along this path here were lighter than this edge right here, then they would already be in this sequence up here. Okay, so there's this E sub j that necessarily has a greater weight than E sub k. Now here's where the contradiction comes in. I'm simply going to create a new tree that is going to be the minimum spanning tree, the supposedly optimal minimum spanning tree, but I'm going to take away E sub j, right? I'm going to take away this edge right here, and then I'm going to replace it with this edge over here, right? So I'll add E sub k, right? Now, because of the way that we set this up, and that it implied basically that the weight of this edge is strictly greater than the weight of this edge, then we've formed a new minimum spanning tree that is better than supposedly this MST over here. One, why is it a spanning tree? By taking out this edge over here, we have effectively disconnected A and B. There's no other path connecting them. Otherwise, that would have formed a cycle. So by taking this out, we've disconnected A and B. But by adding this one back in, then we've connected it, and we would have cut this tree somehow by rejecting this, and now we've repaired it by adding this one back in, E sub k over here. Right? Not only that, but because the weight is strictly less than the original edge over here, it must have lesser weight overall. Therefore, contradiction. MST was not minimal because we were able to build a new tree T that in fact uses E sub k, and that was most likely Kruskal's algorithm, right? So we've proven that Kruskals does generate a minimum spanning tree. Remember, we are on Piazza, and I have YouTube going, so if you've got any questions or comments, please go ahead and make them known. Otherwise, that's the proof, right? So, Kruskals, correctness, right? It was a proof by contradiction. Right? You'll find that a lot of proofs of algorithms are like that. If it seemed, excuse me, let me go ahead and go back to our notes here. If it seemed like it was kind of a trivial proof, it kind of was. I mean, all you had to do was set up a contradiction that, I mean, it seems obvious, at least to me, it seems obvious Kruskal's algorithm is going to generate a minimum spanning tree just because of the greedy choice, right? But it does require a more formal proof, and it's just a formalism of our intuition that we formed that when we ran the algorithm. Of course, if you choose minimum, and then reject it if it doesn't induce a cycle, you're probably going to come up with a minimum spanning tree. But it does require a formal proof, and that wasn't nearly as formal as you can get. You can find some Kruskal's proofs out there that go on for 2 or 3 pages, but I gave you the basic idea there, and it was sufficient for at least for this course. Okay. Still no questions, so let's go ahead and look at the second thing that I wanted to mention here, which is how do you get the efficiency of Kruskal's algorithm? And that was going to require an introduction of a new data structure, a disjoint set data structure. Remember from last time I said that that if you naively use BFS DFS to detect cycles, then you're going to get order n cubed in the worst case. If instead you use this alternate data structure called a disjoint set, then you can actually get this down to order m log m. And with m being at most n squared, this is an improvement, a polynomial improvement, basically. Then you'd have n squared log n at worst, right, with this data structure. So what is a disjoint data structure, right? It has one main purpose, right? It maintains a disjoint set of elements, right? And ultimately, combines them all as a union, right, into one set. So if you've got these 5 different sets, eventually you're going to collapse them down into one set, but it's going to remain disjointed the entire time. I've got this set over here, I've got this set over here. If I take their intersection, it's going to be the empty set. In other words, A, B, C, D, E, F, there's not going to be anything in common between those two sets. Okay, that's what we mean by disjoint. Right? And it's a perfect application here for Kruskal's algorithm because you want to keep track of, you don't want to do a full cycle detection. You want to just say that, okay, here's this edge E connecting A and B. Are A and B already connected, and are they already in this set over here that we've already built? If so, then there must be some path between them. And so we don't have to go and find that path or verify that path. Simply just say, no, that would, if you added that edge, that would induce a cycle. So don't do that. Right? And so it's a much simpler question than just asking whether or not these two vertices are connected. You're asking whether or not these two vertices are in the same disjoint set. Okay. Ultimately, these sets are represented as trees, right? But there may be an arbitrary number of children, and we only maintain references to the parent node. Right? It's not a binary tree, and you can have more than one child. In fact, you can see a preview here of the visualization. 3 has 3 children. Some of them have 1 child. Some of them have no child in their leaves. So it's not a binary tree. It's not a binary search tree. There's no ordering to it whatsoever. And we only keep track of the parent node. If we had to keep track of all the children nodes, the child nodes, then it would kill our efficiency. Okay, so we're only going to keep track of the parent node. Each set is identified with a representative, and that's going to be the root of the tree. So for example, in the, over here, let me go ahead and zoom in if I can. There we go. We've got 4 disjoint sets. Now this is this visualization. We've jumped into the middle of it basically, where we've already done some combinations and unions and stuff like that. And now we've got 4 disjoint sets. And you can verify that really quick. 0, 1, 2, 3, 4, and 10 are all part of one set. None of those appear in any of the other sets. Each set is represented by its root. So in this case, 3, 5, 6, and 12. Okay. So there are several basic operations that we're going to want to support. One of them is, of course, initialize. Right. Right. It creates a single node tree. Right. We call them seeds or whatever you want to call them, where U is the representative. In other words, if you only create one single node tree, then by definition it's going to be its own root. So it's its own representative, and U, of course, is checked to make sure it is not part of any other tree. And I'll talk about checking here in just a second. Okay. Not only that, but we will also maintain a reference to each node to provide random access. Right. Now, this is just a technical detail that we're not going to actually visualize or anything like that. But I'm going to ask questions about where is 10, right? What is the representative of 10? To be able to jump to the node 10, I'm not going to start at the root and traverse and do a pre-order or in-order traversal. That would kill my efficiency. Instead, I'm going to maintain like a hash table or an array that at index 10, you can find a reference to its node. From that node, I can go up to the parent. I can go to the parent of the parent. I can do whatever I need to do. So that's just a little technical detail in an actual implementation. If you were to do this as an implementation, that you would still need to consider. But we're not going to consider that in our analysis. That's just a technical detail. Another operation is going to be the find set. All right, U. All right, it returns the representative of the set containing U, which set it's in, basically. In other words, it's going to return the root of that thing, right? And again, to be able to do that, we're going to have to have immediate random access to the node data structure that represents U. So if I'm going to ask a question about 10, I'm going to have to jump to that node 10 over here, right here. And then I'm going to have to be, and you can imagine what it's going to look like. I'm maintaining references to the parent only, so there's only one thing I can do. I can go up to the parent. That parent has a parent. So I keep going until I reach the root node 3, and my answer to the question of who's the representative of 10, it's 3, right? By simply just traversing up, okay? Another operation that it's going to support is same set. Same set of U and V. And this returns true if both U and V are in the same set, i.e. if they have the same representative. All right? And this is also easy. All you need is 2 calls to find set. All right? You get the representative of U, the representative of V, and then are they equal? If so, they're in the same set. If they're not, they're in 2 different sets. Right? Think back to Kruskals. I'm asking these endpoints in this edge, are they in the same set, A and B? Well, find the set corresponding to A. Find the set corresponding to B. If they're equal, then they must be in the same set, and so you don't take that edge. Otherwise, if they're not, then do something else. Right? That something else is eventually, if I connect these 2 edges, well, you can take that, these 2 vertices. Go ahead and take that edge. That will collapse everything in this subtree and everything in this subtree into one tree. So I need to be able to do that with my data structure here. In other words, I'm going to be doing a union of U and V. Right? This combines the set containing U and the set containing V into one new set. Right, containing everything, right? So that's what a basic union is, right? So here are the keys, or essential details, right? When unioning 2 sets, we always attach the smaller, that is shallower, of the two trees to the larger, right? And what do we mean by shallower or smaller? Or smaller, excuse me. We mean, again, smaller means shallower. In other words, the one with the least height or depth or whatever. The shortest tree is the smallest one. And then we take another tree that is larger, and we always attach the smaller one to the bottom of the larger one. And that's all ultimately we're going to do. Like if you want if you want to union U to V, what you're going to do is you're going to find the tree represented by U. You're going to find the tree represented by V, and you're simply going to take the root of U's tree and attach it to the element that you just searched for in V. Right? So you're going to take these trees and combine them, and we'll see that visualization here momentarily. But you're all in order to get this efficiency out of this data structure, you always have to attach the smaller one to the larger one. Okay, if you attach the larger one to the smaller one, it kills you because it kills your efficiency because everything is going to be dependent on the height of these trees. Okay, and we're also going to add this little optimization step. So this is going to be more efficient if all the trees can be kept shallow. We don't care about the structure of the trees because it's not a binary search tree. We don't have to maintain that all the keys are less over here and all the keys are greater over here. It's not even a binary tree. We don't have to say that that it has two children, two children, two children, and so therefore it has a depth necessarily logarithmic. We can take a tree and we can squinch it down. We can squish it down so that ideally all of the leaves will be at the same level. It's just one node and then all these children down here. Because that's a constant depth. If you find the element that you're looking for, you jump to the parent, that's immediately the root node. You're done, right? One step to determine whether or not an element, the set that the element is in. So our optimization step here is that every operation that traverses up the tree will also collapse it at the same time. So what do I mean by that? Let's go ahead. We can come back to this visualization later here. But what I want to do is I want to show it to you in a little bit of a pictorial form here. All right. So first of all, again, so suppose that we have this tree, and suppose that it is a binary tree, right? And it looks something like this, right? And suppose that we have this other tree over here that has these three elements over here. And now when I take the union, that basically means say that I'm going to take this smaller one over here, and I'm going to attach it to the bottom somewhere to the bottom over here. So if this is U and this is V, or here, I'll even suppose that V is down here, right? If I'm going to take a union of UV, I always attach the smaller tree to the end of the larger tree. And so what that looks like is me simply taking this and appending it to the bottom there, right? Now, you can't get rid of U here, so technically you'd have to do something like this, okay? So that's what a union looks like visually. But what do we mean by this optimization step here, right? So suppose that I'm searching for X here. Right? Now, to get the, I immediately jump to X, and then I traverse up the tree until I get its root, and that's the representative, right? But while I'm going along here, I don't need to, I can do something else. What I can do is I can say, well, it would be much better if this tree were actually collapsed, right? What would that look like? Let me go ahead and label these as A and B. And then this of course is the root up here. And then this thing over here is C, just so that I have a name for it. What I can do is I can make it so that A, in fact, I only need to do it here for X and B. I can make B and X direct children of R. Right? So what does the resulting tree look like? And again, I can do this because if I start here, I can go ahead. I haven't gotten to the root yet. But what I can do is I can basically do two traversals, or I can keep track of everything into an array or something like that. But what I can do is I can say, okay, once you've found the root, go ahead and make X's parent the root immediately. So C is still over here, undisturbed. But I can then make X a direct child of the root. And I'm not changing I am changing the structure of the tree, but I'm not changing the implication of the underlying disjoint set. X is still in there. Right? I'll do the same thing for B. Make B into this direct child of R. Right? And remember that B still had this thing hanging off of it, so now it's over there. A is already a direct child, so there's nothing to do there, but it did have this thing hanging off of over there. Right? And you can see that I took this tree that was of 1, 2, 3, depth 3, and I collapsed it into a tree that is depth 2. Right? And if you do this throughout the algorithm, always making sure that as you go along, when you find an element, when you detect whether or not two things are in the same set, when you're taking the union, as you travel up this tree, making sure to collapse it each time, that means that ultimately it's going to be at most log n, but in practice with this optimization, it's actually going to be some constant. It's not actually a constant. It tracks with this thing called the inverse Ackermann function, which goes beyond our what I want to cover in this course. But basically, for all intents and purposes, it can be treated as this constant sitting out front. So in other words, that the depth can be of all of these trees could be considered constant if you really, really wanted to. I mean, that's true for like any tree with more nodes than the size of the universe or something like that. So because of this slow growing Ackermann function. What I want to do now is show you how this works with this interactive tutorial, again from visualalgo.net. So this basically jumped into the middle of the algorithm at some point. It's actually costly in order to add additional nodes. So basically, what you do, the whole point of using this is that you set everything up at the beginning where everything is its own node, right? And then you start combining things. So let's go ahead and see what that union actually looks like. Well, actually, let's go ahead and find out same set here. No, let's do union first, because same set is going to start collapsing things for us, and we don't want that yet. So let's go ahead and union two things together here. Let me go ahead and union 10 and 9, right? And let me go ahead and slow it down, all right? So the first thing that's going to happen is that we have to find the representatives of those two sets. We start at 10, we traverse up and find that its representative is 3. We're going to do the same thing for 9. By the way, before that happens, you'll see that that collapse just happened. Let me go ahead and go back one step here. Can I? There we go. So we traversed from 10 to 4 to 3. 4 was already a direct child of 3. So we're going to optimize this a little bit by collapsing it down and making 10 a direct child of 3. All right, there we go. It didn't have any effect on the other branches. In fact, it didn't have any effect on the overall depth. It's still 2. But it did have an effect with respect to 10. Next time we search for 10, it's going to take one fewer comparison, one fewer traversal in order to find its representative. All right? Now we're going to do the same thing for 9. We find 9. We traverse up to its root. There's not going to be any collapse here because you can't get any better than a depth 1 tree here. All right, but we did find its representative. Now it makes a choice. Now R here stands for rank. It's most implementations don't keep direct knowledge of the tree's height because if you'd have to update it every single time. For example, when we collapsed 10 into a child of 3, we don't know whether or not we reduced the depth / height, but we didn't make it any worse, right? So rank is basically an estimate on, it's an overestimate on the height of the tree. So rank here is 1. The rank on 2 on the tree with 3 is 2. So we're going to end up attaching this smaller tree here to this tree over here. And let's do that. Combine those two as a direct child over there. All right. Great. And it's done, I believe, right? Yep, we're at the end here. Let's check for, I don't know, find set. We'll find the set represented by 4. Right? And again, the idea there is you just traverse up to the parent. No collapsing happened here because 4 was already a direct child of that data structure. But let's go ahead and take a look at finding the set for 0. All right. Oops. 0. There we go. And here a collapse will occur at the same time that we found its representative. All right. All right. Let me know if you have any questions on that. Otherwise, you can play around with this visualization yourself. And we're not going to go through a full analysis here, but basically the efficiency depends on the height of the trees, right? at most, the height is going to be order log n. There we go. There we go. In fact, in practice, what you can do is you can come up with this, that the height is going to end up being this very, very small inverse Ackermann function growth, which for all intents and purposes, you can essentially ignore, right? So therefore, overall, the amortized cost of searching, of combining, etc., is order n. Right? It's going to be linear because what the situation here is that you start out with n nodes, and you do a series of find set, same set, union. Eventually, you get down to one tree, right? The amortized cost of that. In other words, what's the cost over the lifetime of the data structure? That we're going to do all of these operations. We're going to do, say, m find operations. Why m? Because that's the number of edges in the graph, remember? So we're going to do these m find operations. We're going to end up doing n combine operations because you eventually, you start out with n trees, and then you start combining them and collapsing them down into one tree. So you're going to do order n of these unions. You're going to go from 50 nodes down to 50 node single node trees down into one tree. You're only doing n union operations. So some of them will be more costly because your trees will be deep. Some of them will be less costly because your trees will be shallow, right? And they get shallower and shallower as you go along. If you take the average cost, though, if you divide that by the n operations that you ultimately do, then each one only costs a constant amount. Since you do n of them, it's going to end up being order n. Okay? All right. So no questions so far. So what I want to do is now take a look at another algorithm to solve the same exact problem called Prim's algorithm. Right? And it's going to create a binary search tree, but it's going to do so a little bit differently. The way that it's going to do it is by building the tree out. It works by starting at a vertex and building the tree outward. Right? There are going to be basically three sets of vertices. Vertices are separated into three sets. Right? A tree set. Right? This is the tree we've formed so far. Right? A fringe set of vertices that are immediately are connected to a tree vertex, right? And then the unseen vertices, right? Those that are not yet connected to the tree, right? So what we're going to do each time is we're going to consider edges on the fringe, or sometimes I like to call this the frontier or the frontier, right? However you spell that, right? That looks good. So the idea here is that I've got the tree that I've formed so far. I'm looking at the neighborhood of all of my vertices, and I want to choose one to extend the tree out. Right? And by being greedy about it, what I'm going to do is I'm going to choose the minimum. Right? Among all of these edges, choose the minimum. Right? Update the sets and continue until all vertices are in the tree set. Right? So let's go ahead and take a look at a visualization of this. Right? And let's see. Where's my minimum spanning? I'll use the same one as last time. There we go. There it is. And I'll also start at the same location that I did last time. All right. I'm going to start. I'll run you. I'll go through a dry run here of this, and then we'll take a look at more detail of how to actually do it. I started at an arbitrary vertex A. Now I'm looking at its the things that it's connected to, right? B and D, right? That forms my frontier or my fringe set here, right? There. So this is the tree so far. It's just a single node tree. And this is the frontier. This is the edge, basically. And again, that's the neighborhood of that vertex. And so I'll make a choice here of, well, between 5 and 7. Clearly 5 wins. And so I'm going to update what this looks like. Right? And I'll do that by just simply erasing this thing, right? And extending this out over here, right? Now B is still in the frontier here. It's still in the fringe. But now by virtue of adding D, I look at its neighborhood, and I've added 2 more vertices, E and F. So this becomes my highlighter here. This becomes my new frontier. Right? What about the things that I haven't seen so far? Oh, that's something else, right? These are unseen vertices, right? They're now eventually they will become part of the frontier when I include B, or when I include E, or when I include F. Those are necessarily connected to these 2 other vertices, but that's as the algorithm grows. In the next iteration here, you can look at this frontier, this border basically, and there are edges here of weight 7, 9, 15, and 6. So again, being greedy about it, what I do is I choose the one that's minimum. And then ultimately I update my tree to be that. And then of course the frontier has now expanded as well by including G because of this edge right here. Right? That's the basic idea. Now, how are we going to actually achieve all of this? We're going to have to keep track of somehow we're going to have to keep track of the frontier. And among all of the edges that cross that frontier, we're going to have to take the minimum one. Right? So let me go ahead and set this up, and then hopefully you know the name of this data structure that we're going to use immediately here. I'll leave some room for it, but I'm going to start out at an arbitrary vertex. And I'm actually going to keep track of several things. I'm going to keep track of this triple here, V, P, and W. Right? V is the vertex. P is its predecessor. Right? How can you connect to V? Through P. So in other words, you go from P to V. Right? There's this edge here, and it has some sort of a weight, and that's where my W comes in. W equals the weight of the edge P comma V. All right? So this is the visualization down here. I'm going to keep track of all 3 of these things. Now, let's set this up though. So A, there is no predecessor because that's where I immediately start, and there is no weight, it's 0. What about all the rest of these? All right, now I'm just initializing the algorithm. I'm just starting out here. So I haven't actually taken A into my tree yet. So by convention, what I'm going to do is I'm going to say that there is no predecessor and that it's an infinite distance away from my tree so far because my tree is empty. Right? This is not the tree. I'm going to keep track of my tree over here. Right? And as I take these vertices and their edges, I'm going to move them over to this column. Right? I'm going to eventually have a label on this column that's going to tell you the data structure that we're going to use for it. After a couple of iterations, we'll give it a name. Hopefully you recognize it already. C, nothing, D, E, F, and G. Infinite, no predecessor, infinite distance away from our tree because it's empty, infinite distance away. Right? I'll update these as we go along here, by the way. Okay? So here's my first iteration. My first iteration is I'm going to look at all of these, and I'm going to look at the weights. Right? Remember, we wanted to look on the frontier and choose the one with the least weight. Oops, sorry. With the least weight. So that's what I'm going to do. Visually over here, my tree is empty. There's nothing in it. So my frontier basically is A, and so I expand my my tree set into and to include A, right? And that's simply just going to be me taking this and moving it over here. But I am going to update some things, right? Now look at the neighborhood of A, the thing that I just took. I can now connect to D and B through 5 and 7 as with A as a predecessor. Let's focus first on B. Right? I can now connect to B through A at a distance or at a weight of 7. That's much better than infinite. So let's go ahead and update those things. My new predecessor is A, and my new weight is 7. Here, and if you want to, we can also highlight the tree as we go along here. I think I used pink before. All right. There we go. I won't highlight the frontier. I'll let you do that if you want to. Otherwise, you can check out the book. I do that in the book. We also need to update D over here. Right? So let's go ahead and go over to D. It has a predecessor now of A, and we can get to it at a distance or at a weight of 5. Okay. That concludes the first iteration of this algorithm. Now we repeat until, of course, everything over here has been moved over here, and this is the tree. Right? Now, again, what's my criteria? I'm choosing the minimum one each time. So it's going to be this one now. I'm going to include D into my tree. Right? And I'm also going to mark that we took this edge right here. I will also extend my highlights. There's my tree now. Okay. But I also need to update the frontier here. Right? Now from D, I'm connected to B, I'm connected to E, and I'm connected to F. So I only update if I find a better solution. Look over here at B. From D, I can get there at a weight of 9, but that's not better than 7. So no update there. From D, I can get to E with a weight of 15. Right? Well, that's better than infinite, so let's update that. 15. And my predecessor here now is D. I'm keeping track of that so that I can build this tree as we go along. And from F, I see that I can get there at a distance or at a weight, excuse me, of 6, right? By coming from D. Right? And now if you wanted to take a look here, anything that's not infinite, E, F, and B, that would be my frontier right there. Right? Those are the vertices I'm going to consider next implicitly. Right? I don't have to consider C and G because they're still infinite distance away, or infinite weight away, I should say. All right, next iteration. The minimum has been updated here. It's going to be this one. And so I bring that over to my tree. I will mark that I actually took this edge right here. I will extend my highlights here, and this is my tree now. One thing to note here, in contrast to Kruskals, is that Prim's is keeping track of a connected tree at all times. With Kruskals, you could have this forest. That forest eventually coalesces into one tree, but with Kruskals, you have the property that you always have a tree. Okay? Look at the neighborhood here. There's no use in looking back over here. If I were, F is connected to D, but D is no longer over here, so I would ultimately ignore that edge. I would pay attention to these edges over here, though. F is connected to E, and F is connected to G. F is connected to E with a weight of 8. That's better than 15. So, update this, and my predecessor now is F. Oops. F, and a weight of 8 to get to E. I can now get to G with a weight of 11 from F. Right? And now I've exhausted this neighborhood over here. Okay? Next iteration, I choose the minimum, and so that's going to be this guy right here. Right? Fix this. I drag that over accidentally. Right? And I update its neighborhood. Right? So from B here, I ended up taking the route from A, and I will highlight this as well. And there is my new tree. Right. I look at the neighborhood, but I really only need to look at the neighborhood extending out of this. So C and E. C I can now get to at a weight of 8, so that's better than infinite. From B, again, the predecessor here. And to E, I can get there at a weight of 7. So I'm going to go ahead and update that as well because that's better than 8 from B. All right, next iteration. But before we do that, again, what are we grabbing each time? We're grabbing the minimum one each time. What data structure could we use to do that and to keep track of the minimum? Put stuff in, take out the minimum each time? A heap. In particular, a min heap. Right. I've taken out E, and remember that its predecessor was B, so we end up here, right? And we've extended our tree out, right? There we go. Now we look at its neighborhood, but we only really need to pay attention to C and G here. So to C, I can get there with 5. That's better than going through B. So I will update this to E and 5. And to G, we can get there with a weight of 9, which is better than 11. So I will update E and 9. Right. Next iteration, I take out C. There we go. And I'm connected from E, and I'll extend my tree out like this. Now, looking at C's neighborhood here, it's not connected to G, so I end up not updating this, and on the last iteration, there's no, oops, undo that. On the last iteration, there's no checking or updating at all. It just gets pulled over here, right? And that visualization goes down here, and now I've included everything in my tree. Okay. You're free to add those up. 11, 14, 25, 39. Right? Total is 39 here. I think that matches. In fact, I think it's the exact same tree as produced by Kruskals. There's not necessarily a guarantee on that. It just happens so on this one example. Still no questions. So let's go ahead and develop the pseudocode together here. Okay. I don't know that this is necessarily in the notes. I wrote a new one here to reflect a little bit more efficient way of doing this. But let's go ahead and put it together here together. Prim's MST algorithm. Hopefully I have enough room here. If not, that's all right. We can go ahead and go to another page. The input is going to and the output are going to be the same as Kruskals. G is going to be a weighted undirected graph. All right. So what we're going to have to do is initially, here, I don't want numbered like that. I'll save the numbering here. H is going to end up being a min heap. Initialization. All right. That holds triples V, P, and W, right? And again, those are labeled as before. This is the vertex. This is the predecessor. And then this is the weight of edge P, comma V. Okay? The fringe or the frontier, whatever you want to call it, right? That the predecessor is basically in the tree. That's the idea. The vertex is the thing that you are maintaining. And so V, and then P, and then this is the weight of that edge. And visually here, this is the fringe, and this is the tree. All right? That's the idea. I'm going to go ahead and initialize the tree to an empty set and an empty set. Right. Now this is the vertex set of the tree, which will eventually be the same vertex set as the graph. This is the edge set of the tree, which will not necessarily be the same edge set as before. It's going to be the tree edges instead. All right. Now what I need to do is I need to set myself up. So what I will do, that initialization, basically when I wrote everything in this column right here, now I need to do that initialization step here. So h.enq v1, it's an arbitrary vertex, no predecessor, and 0. Right? So this is the arbitrary start vertex. Right? No predecessor, and 0 is going to be the weight that you can get to that vertex to start out with. That just forces it so that we chose it first when we pulled it out of this heap. Okay. The rest of the stuff for each other vertex, say vi in v2 through vn, those are all the other vertices. We're going to enqueue them, but we're going to enqueue them as vi, no predecessor, and an infinite flag value to indicate that it's not even on the fringe. We have it's so far away we can't even get to it yet, so we're not going to consider it. So again, this is the initialization. There we go. All right, now we go into a while loop. Right. While h is not empty. Remember over here with our simulation, when did we stop? Well, when the last thing was out of the heap, and then we formed a tree basically. All right. So I'm going to get the next thing out, right? Which is going to be, I'll label this as x, p, and w. All right. There we go. And that'll be h dot dq. There we go. So I basically just when I circled something over here and then I brought it over here, I'm dequeuing it. Okay, and I'm giving all those things names so that I can work with them. All right. I will want to now look at the neighborhood of x. Right. But before I do that, let's go ahead. Oops. Let's go ahead and update our vertex set. V sub t union x. Right. Yep. And E sub t will update E sub t union x p. Right. Basically, I am adding a vertex here, the vertex to the tree. These are tree vertices. That's why we've got the subscript t here. And we're adding this edge here to E sub t. I'll annotate this up here. This is V sub t, and this is E sub t. How do I do that over there? Yeah, okay. You know what? Let me go ahead and rewrite it so that it's absolutely clear. V sub t is, or t is simply going to be the tuple V sub t, E sub t. And I'll initialize it to the empty set and the empty set. Right? And then I'm adding stuff down here to it. Okay? Now, unfortunately, I'm running out of room, so I'll go ahead and dot, 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 come back up top here. And for each element y in the neighborhood of v, x, sorry. There we go. I will do an update. So this might be new, and we're going to talk about it here in a second. I will update priority of y. I've run out of horizontal room here now. X and w of x comma y. There we go. There. And then finally output t. Now what am I doing here? Right? what I did was I looked at the neighborhood, say coming from B here, and I said, okay, well, I can get to C now with a weight of 8. And so what I was doing over here in the heap is I was updating that priority, right? And visually, of course, it was just me erasing these things and updating these things. But how does that actually work in an actual heap? Okay. So let's go ahead and look at an example, and then I'll go into the details of how it would work. Oops. Let's see. Where's my min heap? There it is. Okay. Now suppose that I were able to magically jump to, say, I don't know, 55. Right? Can I update its priority? Say that I'm going to go ahead and transform 55, and I will transform its priority into something else entirely. Just want to make sure that it's not in there. 3. Right? How would we go about doing that? Well, first of all, you have to get to the node containing 55, and we'll talk about that little detail here in a second. But what you can do then is you can update it. So instead of 55, it'll be 3. Right? Now, is that a min heap? No, it is no longer a min heap. Right? We've violated the heap property. Look to its parent, and remember this is a min heap. That's why the minimum element is always at the top. That's okay. Remember, when with heaps, when you put something in, it doesn't necessarily maintain the heap property. When you add something over here, you just added it to at the end maintain that fullness property. You might have to heapify it up as you go along to maintain that heap property. Same idea here. This property has been violated, so all we need to do is heapify it up or heapify it down. I see that I changed it and I made it less. So necessarily, since this is a min heap, if it has to change, it has to go up. I see that 3 is indeed smaller than 5, and so I exchange them. I swap them out. Swap. All right. When I do that, I'll go ahead and animate the next step here. So that's going to be 3 and 5. Remember that. Now I'll go to red, 3 and 5. There we go. I might potentially have to continue all the way up until the root. In this case, I don't, because 3 is less than 1, and so we're good to go here. I did have to swap these two, though. Right? What if I had changed it to something else entirely? What if I had instead increased the priority? Decrease, increase, it all becomes confusing because it's a min heap. So increase in the priority, in other words, going from 55 to, say, 75, right? That you're increasing the value, but you're also at the same time decreasing the priority, basically, right? If I put 75 in here, right? Obviously, this is no longer a min heap because both of its children are less than it. So simply promote the minimum of its two children. Swap. And I get, in the end, I think 70 was there, and 75 is now down here. Right? So I just have to fix the heap each time, which is still going to be order, height, or depth, which is going to be order log n. That, of course, assumes that I have magic random access to get to this element. That can be taken care of just like we did with the disjoint set data structure. You maintain another data structure with random access to those nodes. So given this this triple or whatever, we want to, and it's in the heap. We need to be able to jump to it, its location in the heap, change its priority, and then either heapify it up or heapify it down. Right? That can be done very easily just using a regular old array with random access. It can be done even easier if you use some sort of a hash-based data structure like a hash map or something like that. Okay. So let's go back over here, and as our final step for today, let's talk about the efficiency of this heap-based Prim's algorithm, which is for minimum spanning trees. Right. So efficiency. All right. So first of all, updating the priority of a single node element in the heap is order log n. Right? And is possible if we maintain random, that is free, access to each node in the heap. Right? If we have to go searching through the heap, either using linear search if it's an array-based implementation, or if we have to, if it's a tree-based implementation, we have to use in-order traversal or something to find the node we're looking for. That kills our efficiency. Right there, that goes from log n up to order n. All right. So we don't want to do that. We want to maintain this this other set of data structure where we can. I want the element corresponding to priority 5. It jumps to that location, and I can change its priority to 3 to bubble it up, to heapify it up or heapify it down. All right. So again, it can be it can be maintained there. Okay. What about the overall complexity? Excuse me. Here we go. So, the initialization is trivial. Right? In fact, you put everything. Put the first vertex at index 0 in the heap. All other vertices in the heap have equal priority and don't need to be sorted or inserted. Right? You just throw them all in as is because everything is going to be infinite at the beginning. Okay. Once you're there, though, each operation of get min, everything's already in there, so you're not putting stuff in after that. Each operation of get min and update priority is order log n. Now you can use some more amortized analysis here because the heap does get smaller over time. As it gets smaller over time, n decreases. N here is the number of things in the heap at any one time. At the beginning, it's going to be n, so it's going to be log n. But that gets cheaper as you go along because there are fewer and fewer things in the heap. We take them out, we never put them back in. So you could do a little bit of a amortized analysis there. It's not going to buy you much, though. Okay, and if anything, it's going to be the same order, basically. How many times do we do each operation? Get min is called n times, order n times. Yeah, n times. All right. Update priority is called how many times? Right. We update the priority potentially by looking at this new, by including this edge over here, or this vertex over here. We look at its neighborhood, right? So we may have to update. Even if we're not actually updating, we still have to look at it in the heap in order to say that, okay, well, I'm not going to update that because it has a higher priority or a lower priority, and it does not need to be changed, right? We saw that several times there. So some of them could be free, but let's go ahead and consider the worst case scenario where we're always updating the priority. It's always going down for some reason. So update priority is called once for each edge, right? But then again, once for each edge, right? Technically, each vertex is examined a second time, but no update occurs, right? Remember, this is kind of the handshake lemma. If I've got A to B, if this is the first time I've seen it, I'm going to update that priority, right, based on this edge. Now, the next time I see that edge, I'm going to look at it from the perspective of B. Do I need to update that? Well, I'll look at that and say, well, that's not even in the heap. It's nil, so I'm not going to end up updating that. So, but that is a constant operation there. But it's not going to end up with the order log n operation of fixing the heap. So no update occurs, and we can effectively ignore it. All right. So overall, m times. Right? In total, we have that there's going to be n plus m heap operations. So log of n. There we go. I'll go into full math mode there. All right. N log n operations for pulling out the minimum and fixing the heap. M log m. In fact, let me rewrite this so that it's absolutely clear. There we go. There we go. All right. So n operations, n get min operations here, each one which is order log n. M update operations, which again is order n log n. Now remember that this is what we're trying to do here is we're trying to create a minimum spanning tree. So if it's a disconnected graph, we can either immediately reject it, or if there are fewer than m or fewer than n edges already, we know that we're going to create this forest, or we know that it's either trivially already a tree or acyclic or something like that. So the point that I'm trying to make here is that m is much bigger, right? Generally. If it's not, then you've got this kind of trivial case over here. So ultimately, this is going to simplify into order m log n. Right? If you use a correct data structure here of using a min heap as your priority queue to put stuff in and take stuff out. Okay. With respect to the size of the edge set, that's going to be essentially linear. It's going to be quasi-linear, if we want to call it that. But unfortunately, you're not going to get much better. I mean, you have to examine all the edges to determine, is this thing, should this be in the minimum spanning tree or not? I can't ignore a whole bunch of edges unless I'm doing some heuristic or exploiting some other structure of the input graph. All right. All right, I'm not seeing any more questions here, so that's where we'll go ahead and end it for the day. Tomorrow, we're going to be looking at 2 algorithms. I'll present them in full, and then we might look at the details later on. But 2 algorithms for minimum distance. That is, given a vertex or given 2 vertices, I want to find the minimum weighted distance or the minimum distance to get from A to B in the graph. Right? And we're going to look at one algorithm is going to look very, very similar to Prim's here. That's Dijkstra's algorithm. But instead of only considering the weight that connects from the tree to the fringe, we're going to consider all the weights that got us there to begin with. Okay? All right. Have a good day, and I will see you in office hours.